Welcome back to the third track of CPP Russia. The second day of conference is going right now, and we are going to hear a talk about transcoding in C++23. The expert for the talk would be Timur Dumler, a C++ developer specialized in audio and music technology and an active member of the ISO C++ community. Timur, you have the floor.
Hello, everyone. My name is Timur. Thank you. So my pleasure today is to introduce JeanHeyd Meneide, also known as the PhD, who is our speaker today. He's representing the consulting company Shepard's Oasis. He's also studying software engineering at Columbia University in New York, and he likes dogs. Hey, JeanHeyd, great to have you here. Obviously, you're also known for the Sol 2 library, which actually I have also used myself, which I can say it's a really fine piece of software. So that's good stuff. And obviously, we know each other as well from the C++ committee, where you're contributing a lot to the new C++ standard. So yeah, it's great to have you here tonight.
Yeah, I'm really happy to be here. Thank you so much for those kind words. I'm really happy to share with everybody here something I've been working on for making Unicode and making encoding and decoding and all those operations that typically tend to mangle text somewhat a lot safer and a lot easier to use in C++. And so I very much hope that you enjoy the presentation, that you enjoy the work, and that you learn something from it that could help you in your career or your workplace today.
Good morning, afternoon, or evening, everybody. My name is JeanHeyd Meneide, and what I am here to do is to talk to you about burning silicon, or essentially speed for a text transcoding API in C++. So, first off, if you want to be a part of this, and you kind of want to follow along, there are several parts that came before this, but you don't actually need to watch any of the parts before this because I will take you through almost all the irrelevant pieces that will help inform you to do this. But I will make references to the other talks because each one of them delves into various different portions of the API and some design and technical aspects of the API. So the first one was a CPPCon 2019 talk, and that talked about basically an overview of the whole thing. The Meeting CS was 2019 talk was a little bit different. It talked more about the general transcoding aspect. And the other API here was just the one from Pure Virtual C++, which was just a short while ago, that talked about how we prove the basis operations to get the things we want overall in this API. So particularly in part 3, we prove the math for the basis operations, right? We prove that if you have an encoding alpha and beta, or beta, that you could take a small set of basis operations and you could essentially do everything you need to do that you would want to do with text, right? So you could encode, you could decode, you could transcode, which means going from the code units of alpha to the code units of beta. You could validate code units that were in a body of text. So you could say, like, is this UTF-8? You could validate code points in text. You could say, like, something like, can these code points be ASCII? You can count code units from code points. So you can ask, say, what is the number of big 5 bytes in these code points, right? In these Unicode code points. And you can also count code points from code units, right? So you would figure out the number of, say, code points that come from a UTF-8 sequence, right? So if it's an emoji and there's only 3 bytes, you might end up with one. There's only one code point out there. It's only one emoji. Or if you have 4 UTF-8 bytes, you might end up with, say, 2 ASCII bytes and then 1 double byte sequence that encodes a typical Chinese character, for instance. And so that is part of what we proved in part 3. So to give you an example, here's the bog standard basic UTF-8 using this lucky 7 ideology, right? So here we have a struct it's called UTF-8, and what it has these 7 pieces, right? So we have the code unit type, which is car8t. We have the code point type, which is car32t. And we have the state type, which right now is just an empty struct because all Unicode encodings are actually they don't really require any shift state or any additional memory, so we just have this empty struct here. And these are the 3 type defs you need. Then you need 2 static context spur variables, integer variables. And what those tell you is the maximum number of code points that an operation can yield. And so in this case, it's 1, right? When you decode some UTF-8, when you finish reading a single block of information out of that UTF-8, you end up with 1 code point at most. And max code units, right? You can read up to 4 code units. Now, the actual UTF-8 encoding itself can actually read up to 6, but that is actually unsafe and provides what's called an overlong sequence attack that can happen in certain scenarios. So it's actually limited to 4, because you don't want identical overlong sequences mean the same thing in your UTF-8. And then the last 2 things here are literally just two member functions here. Sorry about that. Encode 1 and decode 1. And encode 1 and decode 1 encode 1 basically just takes in code points, which in this case is the span of car32t, an output span, which you write into, which takes the output. It takes the current state variable, which in this case is an empty struct, but that's our current state. And then we have this encode error handler type, which is an error handler if something goes wrong, right? And it's identical for the decode 1 function here as well. It's just kind of reversed, right? The input is instead car18, and the output is instead U32. It's a U32 span to put out Unicode code points, right? And then you have the same state and current variables, and that's what an example encoding object looks like. To continue on that, one of the other things that is important here is that you can also capture more exotic encoding objects, right? So here we have a Big 5 Hong Kong supplementary character set, right? And this is one of the encodings that is used, in Taiwan and related places. There is a code point type or code unit type, which is just our car. There's a code point type, which is just car32t, right? So it takes in sequences of car and it outputs sequences of car32t, and we state it's just the empty struct still, so that's fine. But the interesting part here is this part, right? There's 2 and 2, right? So Big 5 with a Hong Kong supplementary character set, most Big 5 encodings are double byte character sets, or double byte encodings, right? So there's 2 bytes, and each of those 2 bytes makes up a character. Now, you can pair your Big 5 with a single byte encoding, right? So you generally it just goes with ASCII, but you can also put maybe even EBCDIC in there if you really wanted to. You put an ASCII-ish form of EBCDIC. But the whole point here is that you can actually output 2 units of information here. So there are 5 cases in the Big 5 Hong Kong supplementary character set that when you decode, it specifically produces 2 code points, right? So instead of only being able to output 1 code point at a time, you can output 2 code points at a time, right? And that's how you signify, and you set this max code points variable to signify that. Max code units is just 2 because again, this is a double byte encoding, so you can have up to 2 cars that represent the characters you're interested in. And then you need you have an encode 1 and a decode 1 that take in the inputs and outputs. It takes in the inputs, writes the outputs. You can have the state, obviously, in this case, it's an empty struct because there's no shift state for Big 5. And you have your error handlers for the encode and the decode. And so I've been kind of throwing a lot of these like encode error handlers and these are encode results and other stuff. I just kind of been glossing over them because I do explain it multiple times in previous talks, but we'll go over it a little bit. So, in case you were lost, right? So C-span and U8 span, U32, they're just stood spans of car IT, car3, right? They provide you a view of contiguous data, right? So it says you can look at an array, you can look at the data of a vector, you can look at, all sorts of things. But it's a contiguous block of memory. You can think of it as a pointer in a size. We also have an empty struct here. Because again, it's just an empty struct, is literally, that's all it is. And then we have this encoding error type. And what this enumeration type does is that it gives us basically 4 ways of signaling that something went wrong with our operation. So the first is okay, right? And that's just, everything's fine. Then you have invalid sequence, which is basically to say, you gave me a sequence of text that is not allowed by the encoding, right? So I read a byte and it was wrong and I didn't expect it, and so you get an invalid sequence, right? And that's how that works. There's also incomplete input, where you say I'm working with Big 5 Hong Kong supplementary character set, HKSES. And you give me the first byte of a double byte letter. Then the input stops, right? I have no more input left. At that point, right, you didn't give me anything wrong because it was a valid starting byte, but I need a second byte. So what I return to you is incomplete input. I say, listen, you didn't give me enough. Then there's also insufficient output space, which is where I've read through the input, it's all correct and everything else, and I'm ready to give you code points, a sequence of code points or a sequence of code units, and I run out of space, right? So I test, is the iterator I got that I've been incrementing from the beginning of the output, is that equal to the end of the output, right? And if I've reached the end of the output, then I'm out of space, right? So this means that typically we want this to be safe by default, and that's what we go for here. The result types, they're pretty straightforward. They basically just contain an update of all the information that happened during one of the encode 1 or decode 1 calls. So in the case of a Big 5 decode result, we have, we have a C-span of input and a U32 of output. So the car is the input type for a decode, right? So decode takes in code units, which would be car, and outputs code points, which would be U32s, right? So we get an input and output, and we basically get an updated state, right? So if it reads 2 cars, then the input variable that we get back in this result will be moved up 2 cars from what we passed in, right? So we get an updated view of the data. Output is the same. We get an updated view of the data for after it basically shows you the view after what we had written. The state variable is just a reference to the state. So that contains all of the any shift states or anything else that you have. In this case, just an empty struct. We have the encoding error, which is just the error code that tells us what went wrong, if something did go wrong. And we also have this boolean for whether or not we handle an error. And this is important for cases like when we insert replacement characters. And so even in those cases, what we do is we set the handled error flag, but we clear the error code so that further down other algorithms don't trap or bail because it detects that error code is not equal to OK. But we still want to propagate that information that we did handle an error. It's just that we did the replacement character thing, right? We put the little square diamond that people recognize. So obviously we don't want them to stop the algorithm, right? But we still want to let them know that we handled an error anyway. So check your text or something. And then we have an encode result, which is literally exactly the same thing, just except, the input and the output are reversed, right? So we're taking an input of code points, which in this case is U32 span, a span of car32T. And then we have an output of C-span, which is the output of the bytes we want for our encode operation. So we go from code points to code to our cars, to our code units. And as you can see in this little note here, it's really the same for a U8 decode result if we were to do for UTF-8, except that, instead of C-span, we'd use a U8 span, right? Because the input is car8T. And in the encode case, for a U8 encode result, we'd have a U8 span for UTF-8. But then that's it. So that kind of covers the supporting, some of the supporting types here. For the error handlers, it's pretty straightforward. What you do is when an error happens, what we do is we pass you the original encoding, the current result that would happen, and a U8 span. And what you're supposed to return out from all of this is a result type by value. And what this means is that you can take in this decode result thing that the encoding hands you to say, this is what happened, and this is the error, and this is where we handled an error, and this is the current input and the output, and you can manipulate it to be what you want, and then simply return it, right? And we'll just return that out of the encode 1 or decode 1 calls. The last parameter here that you see, the U8 span or the U32 span, what those are is that represents a span of characters that were read, but were not processed. So if I read from, say, an input iterator or an input range, those typically you can't go backwards on them, right? So once I read something out of that stream, once I read something out of that range, it is impossible for me to go back. And the canonical example of this is a stood iStream iterator, right? I can't go backward. Once I read the value, it's out of the stream, it's gone, right? Like, it's a network stream or whatever else. So I can't go back and retrieve it, right? So you need to have, if an error occurs and I don't do anything useful with the things that I read, then I need to hand them back to you so that you can do something with it, right? And so that's what this very last parameter is in all of these functions. It is just a way of signaling that information. And of course, in this case, we have both a U8 for decode and encode, and we also have a big 5 for decode and encode. And it's literally exactly the same thing, except we're taking the big 5 versions of these things, and we're taking the C-span here, and for the inputs that we've read but haven't processed because an error happened. And of course, the encoding at this point is big 5 HKSCS rather than the UTF-8. But it's all the same idea here. Nothing's radically different. But this is basically how the error handled. And again, there's more information about that in the part 2 presentation at Meeting C++, and I go into great detail. But we're just we're giving you a basis so you can understand what we're going to be moving on here with. And of course, a little bit of a plug. C++23 is looking at something called function ref, or it might be called any invocable ref, something weird like that. But basically, std function ref is just a lighter std function and avoids a lot of the mistakes of std function. And of course, it's a reference type, so it doesn't strongly own anything, but it can save you a lot of compile time. And most of the time, you won't need to keep the function around, so there's no point storing in a std function, and you're just better off storing it in a std function. You're just better taking a std function ref as the parameter for part of your encoding, right? So now all of this should make sense to you, right? So we have our code unit and code point types. We have our state type as the empty struct. We have our max code points and max code units, and then we have, of course, our encode 1 and decode 1, right? In this case, we have the encode results that get passed. That gets returned out of the encode 1. We have the decode result that gets returned out of decode 1, and then of course we have our inputs, outputs, the current state, and then our error handlers in case something does go wrong. If nothing goes wrong, then we don't call the error handlers at all, and everything's just fine. And that's okay. And that's our basis. And so this is from the part 1 talk, but it's really expanded upon the part 3 of the talk, where we talk about this basic loop that works for everything and that converts. The presentation says one code point at a time because at the time I was talking about a UTF encoding, a UTF-8 in particular, but it works for all encodings, right? You pass in an encoded single input, you decode that encoded single input, and you get a Unicode code point. Then you take that code point and you go to the other encoding and you ask it to encode that, and then you hand that encoded single output back to the user, right? And that is how you basically do a encoding conversion from encoding alpha to encoding beta without any loss of generality here. And so this is essentially what Lucky 7 was. This is what all of part 3 was about. It was about talking about the 7 operations and how you can use those 7 operations to build everything, right? And so the basis algorithm for this is that if you have an input and you have an output that you can write into, and you have encoding objects, alpha and beta, the loop basically works like this, right? If the input is empty, return, right? You have nothing to do, right? And so you just return everything's fine, and you say everything's fine, right? And that's okay. Otherwise, what you do is you call alpha's decode 1 with the input into a span that is dragged over an intermediate that you make of the code point type, right? So as long as the encoding objects alpha and beta have a common intermediate code point object, right, you can just basically write into this max code point buffers. And again, you will also be guaranteed that you won't get an error about insufficient output by using this max code points. by using this max code points definition right here, right? So because the encoding tells you how many code points you can possibly put out, whether it's 1 in the case of UTF-8 or 2 in the case of Big 5 Hong Kong supplementary character set, you never ever run to a place where lack of output space is a problem, right? Which is technically a problem in many of the C APIs, the single character convergence C APIs, right? So anyway, after decode 1 finishes, you basically check if there's an error, and if there is, then you bail with that error. Otherwise, you call betas encode 1, and you give it the intermediate, you give it a span over the intermediate, and you hand it also the actual output buffer that you're writing out to. And if an error occurred, obviously you bail with an error, but if everything's fine, what you do is you take the result of the encode 1 call, you take the result of the decode 1 call, you set it back into the input to update the input so that you move the input forward by the number of things you read, then you just loop back, and you just keep doing this. Right, and that's the basic of this is literally all you have to do. Some people point out and think that this is novel, but actually, as it turns out, this has actually been present in Icon V for well over a decade. This is essentially, I'm describing to you how Icon V does some work. Now, there's some problems with Icon V, and we'll get to that later, but this is the basis algorithm, right? This is the same algorithm that the Fortune 500 company uses. This is the same algorithm that Ogonek took into account. This is the same algorithm Tom Honerman's text view almost got to, but he didn't quite go all the way and connect all the dots there. But this is essentially how this works all the time, right? And out of this lucky 7 basis, right, out of those 7 members, right, the 3 type defs, the 2 const per member static member variables, and the 2 functions, right, those 7 things, you can build encode, decode, transcode, validate as, which is validating the code, either code units or code points, and the count of an encode and the count of a decode, right? How many code points am I going to get out of this, right? And you can build everything, right? This, again, part 3 goes into this in great detail and explains to you for almost every single one of these things that you see here, exactly how it works. And so, again, you can check out part 3, the pure virtual C++ talk for that. And so basically, right, it's sort of like the elements of programming, right? It's not actually Stepanov, but I imagine old man Stepanov, his masterpiece about the elements of programming and how at the foundations of the STL, right? And so what we've basically described in the pure virtual C++ talk, and that I described to you right now, is essentially the elements of programming, but for transcoding. But it's, instead of being written by a master like Stepanov, it's it's instead written by a derp like me. So this is but this is the elements of transcoding, right? The basis of everything that we predicate pretty much the entire design on. Now, that's fine. Ish, right? I mean, it has some very good properties to it, right? So let's talk about some of the properties that it has. So one of the properties that is operation safe and is optimizable, right? It uses an output range for its write operators, right? So when you saw that Big 5 HK SCS, you saw that it took a span of output, right? And what that means is that it's safe by default, right? And this is something that's actually plagued me because the 3-legged algorithms in standard, like std copy and std fill and things like that, and also the ones in range v3 are not safe. Right, like even the range algorithms, which baffled my mind when I first figured out about it. Right, the range algorithms take either 2 iterators and a single output iterator, or they take a range and also an output iterator. Right, there's no one that takes 2 ranges. Right, so in my case, we prefer safety. Right, so the output range always stops if we reach the end of range. Right, and so if you want to have an infinity range that has undefined behavior, if you overflow, then you have to opt in by specifically marking that with unbounded view. And I talk about this in part 1 and part 3 and a bunch of other parts where I talk about the safety. Also, one of the things we have is an optimized standard that uses iterators and ranges, right? So we don't want to give an output function where you call the thing and you pass in some variable, and then you maybe get a return value out of that tells you if something went right or wrong. It's much better to use what we already have in the standard with iterators and ranges in our entire algorithm. This doesn't mean that you can't build a standard library that's based on functions and sources and sinks, but it's much better to use iterators and ranges, and it's also much easier to optimize for them because you can detect when you're working with bulk direct writes, and so do all kinds of crazy optimizations that almost all standard libraries to this day do when you're dealing with fill or copy or anything like that. So it's very important to take advantage of that and to continue that legacy by using output range to its fullest potential here, despite the fact that range v3 and stood ranges and other things don't do that. One of the other great properties about this that is embedded, it's basically embedded friendly, right? Other solutions might overconsume memory or over-eagerly consume memory, or might allocate when you don't want it to, things like that, right? So the guarantee about the Lucky 7 here is that the algorithms will not consume more than some iterator and view temporaries, right? Some other basic temporaries like booleans, like size bookkeeping, or iterators to track whether you pass the end and things like that. And of course, it won't ever consume more than 2 times the maximum number of code points plus 2 times the maximum number of code units, right? Because for any internal buffering it needs to do, right? And so basically, what I'm trying to say is that it's all stack based. There's no allocations, right? At no point do you need to allocate, right? So this is ready. This has been deployed already on small devices, right? You can put this on an STM32. It works. It's there, right? Obviously, I mean getting a C++ compiler that behaves nicely is a slog, but it works on embedded devices. It works on small devices. We don't leave people who have exceptions off or people who want to work on a low memory environment behind, right? And that is enabled by the Lucky 7 properties, right? Because of the way the algorithm works, it works one chunk of singular information at a time. It will never consume more stack memory than you have available on your machine, right? Because it's not a recursive algorithm, it's an iterative algorithm, right? You never have to use more than you have access to. The other thing about Lucky 7 is that you can connect arbitrary encodings, right? As long as they share a common or convertible code point type, and as long as you have an encoding object that has the 7 basis operations, I can connect your random encoding that you wrote 5 years from now to what I wrote today. Period. There is no compromise on this. Every single part of that work is usable from now until eternity, right? And this is one of the biggest things that makes it suitable for the standard library, but also suitable as a library in general, right? It is extensible, right? You can handle arbitrary encodings into the future so long as they play by the same rules. It is a concept-driven programming, right? A concept-driven library, right? So as long as you satisfy the concepts the same way that decades later, as long as you satisfy Stepanov's concepts for what it means to be an iterator and for what it means to work with these algorithms, those algorithms will keep working. They are timeless, right? And in the same way, the Lucky 7 brings with it a timelessness that makes it far, far, far more suitable to last throughout the lifetime of the standard and everything else. And we have to remember that it's scalable, right? Remember that all you have to do is plug in those 7 basic operations, right? So you need 3 type defs, you need 2 static constants per member variables, right? And then the only thing after that you need is an encode 1 function call and a decode 1 function call. And that's it. That is it. The moment you write that in your program, it extends infinitely, right? So the committee doesn't get to tell you that your encoding is or isn't good enough to support, and companies don't get to tell you what encodings are worth it or not, right? So Microsoft Windows happens to not ship an encoding that you need. Well, it doesn't matter because you can put it in yourself, right? You don't need to rely on the committee or wait for the what working group for the web to tell you what encoding is allowed and wait for the browser to implement it, because you can just do it yourself. you don't have to wait for anybody. And that means that this design is scalable. Not scalable in terms of like, performance, but it's scalable in terms of people time, right? Your time is precious. It is the most precious resource a human being has. And so we need to make sure that all the properties on this are scalable to infinity and beyond. Also, let's talk about the speed. Is this fast? Right? If this was the engine of your car, would this be able to drive you places? Would you be able to get places? No. No. It is not fast. It is slow. So it's correct, right? It's maximally correct. But again, look at this basis formula that we've written for Lucky 7, right? We check if the input is empty. Otherwise, we start this loop. And what we do is we call a decode 1 into a temporary, and then we check if error happens and we bail if they do. Otherwise, we take that intermediate and we call encode 1 and we put it in the output, then we update the input, etc., etc. Where you can see those little exclamation points is where basically the majority of the performance sync comes from, right? So let's talk a little bit about this. The inefficiency is there, right? So the intermediate is not always necessary, right? So in one of the talks, I talked about UTF-EBCDIC, which is a real thing. Look it up. And I used the example of UTF-8. And the idea here is that UTF-EBCDIC has an intermediate step called UTF-8 mod, right? So why would I go from UTF-EBCDIC to UTF-8 mod to the actual UTF-32 code point and then loop back around and start trying to cram that same code point into UTF-8, right? Like I already have the UTF-8 mod step that comes directly from how you decode a UTF-EBCDIC, right? Why would I throw the step out just to create a UTF-32 code point just so I can get to UTF-8? That's wasteful, right? Similarly, UTF-16, if you're in the bilingual multiplane, the first plane, right, the first 65,000 or so characters, right, you can write that directly into UTF-32, right? The non-circuits are directly writable. So why would you bother trying to do some put it in a code point and then lower it down into UTF-32 afterwards, right? Just put it directly in UTF-32. It doesn't make any sense not to do that, right? Same thing with ASCII or Latin 1, right? ASCII is basically bit blastable into UTF-8. Latin 1 is extraordinarily compatible with UTF-8, right? So at what point do we need to go from ASCII to some code point and then lower that down to UTF-8, right? Just memcopy, just bit blast that bad boy, right? And same thing here with ASCII or GBK encodings for China. GB being Weibao being the standard technical standards that come out in China. There is Weibao 18030, which is a encoding that is it's a Unicode encoding, right? But instead of prioritizing compatibility with ASCII or with Latin 1, it prioritizes compatibility with GBK, right? So you can have some very nice and slick shortcuts converting between GBK and GB 108030, right? So again, why would you waste your time round tripping through some common code point when you can just go direct, right? And this is what I mean by the inefficiency that's present in these libraries that we have. So, again, to kind of hammer it in, right? Why am I going to go from alpha's code units to a code point to then lower it down to the code units all over again if there's a direct path to go between the code units and the code points, right? There's no reason for me to do that extra work. So that's one of the problems. The other problem is doing singular one-off conversions versus bulk conversions, right? So in this last slide, we're talking about doing a singular conversion, right? Going from a single unit of information in code units to a single unit of information in code points to a single unit of information in code units, right? And that's still bad because it's a singular operation, right? What if I want to bit blast? What if I had, 500,000 ASCII characters and I was converting it to UTF-8. Well, even if I do a direct conversion from a single UTF-8 code, single ASCII code unit to a single UTF-8 code unit, right, that's still one at a time, right? I want to be able to just basically call std memcopy and just blast that bad boy all into UTF-8, all into my output, right? And so, and this is not something that's a new concept, right? So, for example, the Musil library, Rich Felker, who is one of Musil's maintainers, creators, caretakers, he's actually available on GitHub Sponsor if you want to sponsor him and his work in Musil. He knows that doing a byte at a time conversion is basically roughly half the speed of bulk, right? And so in the quote, I have ... here. The quote goes on to say it doesn't really matter, and we should just write it that way anyway because it's better to have a maintainable code rather than crazy shenanigans. But that performance drop matters for some people, right? You can't just take half of the speed that you get it if you just written something a little bit better, something that optimizes a little bit cleaner, right? And so that's one of the problems with single versus bulk, right? And so let's consider one of the C standard functions to do a singular conversion, right? Which is MBR to WC, right? Which is multi-byte restartable to wide character. And basically it converts one block of char star data to wcar, to a single wcar, right? And the problem with that is that maybe that functions in a shared object or a dynamic link library, right? Maybe it has indirect calls through locale tables, right? Maybe, and again, because it converts a single block into a single wchar-t, right? There's no SIMD to be done on this non-bulk data, right? I can't do anything with that, right? I can't set up a nice vectorized loop and set up my processor and tell the thing to start screaming along because I have all this bulk and thing in the way, right? So especially if it's in a DLL, right? So there's a hard compiler barrier that prevents it from just folding everything up nicely, right? Again, if you statically link, you might get some performance gains, but even still, the single functions still have issues. There's also another issue with singular functions, right? And the same problem is present in Lucky 7, right? You have to do a lot of invariant checking, right? Is the output empty? Has the input been exhausted? All these kind of things, right? And the C standard functions do the same thing, right? Is the destination pointer null? Okay, then this is a counting function. Okay, if it's not null, okay, it's not a counting function. I'm actually going to write things to PWC. Is the input, properly sized, right? Did you follow all the rules, right? Do I need to check, X, Y, Z, ABC, right? So you're basically checking things like, is this null or whatever again? And so when you try to farm this out into the string version, which is MBSR, two wide character string, you basically end up in this lovely situation where you're over and over again, you're checking the same invariants because you keep implementing the string version of these, the multi version of these, in doing single checks, right? And it's the same problem with Lucky 7, right? You're implementing this in terms of a loop that calls a singular function that does only one unit of work. So you're doing a bunch of checking all over again. You're constantly checking your invariants, which is not ideal here, truly. So we could definitely do better, right? So obviously we listed that we can shortcut, our round tripping. We don't have to go through a common code point. We can take advantage of additional information on the encoding object, right? So for example, the UTF-8 mod step that UTF-EBCDIC has allows us to get to UTF-8 much quicker. We can also do anything with pointers or size of the pointer or any contiguous range that we have. We can do single instruction multiple data or SIMD to get faster computation. And we can also check invariants once instead of checking it basically the number of input, at worst case, the number of inputs, the size of the input times, right? Like that's completely wasteful. So what we basically need is we need speed extensions, right? We need to go to a place where we can speed up the basis and go faster than Lucky 7, right? But we don't want to abandon everything that we've built up so far, right? So how do we do that? How do we get to a place where our functions and everything else work out nicely? So remember the basis algorithm, right? We have an input, and you have a writable output, and you loop, and whatever, blah, 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 right? Well, step one is to basically cut out intermediates, right? So for our text input and our writable output for encoding objects alpha and beta, right? If the input is empty, then return. Otherwise, before we do the basic loop, we say, is it possible at compile time, can we check at compile time, is it possible that this magical text transcode 1 function that gives us a special shortcut between alpha and beta, is it there? can I call it? And if so, I'm going to call it. And I'm not going to do the basic loop. And that is and what that basically means is that I've implemented a faster version of going from this encoding to the next encoding, one at a time, right? It's still a one at a time function, but you're basically saying is I've implemented a shortcut here, right? And so if this text transcode 1 free function, this ADL extension point that you write exists, right? Like, so for example, we have an example here of big 5 UA transcode result, and we take a C-span of input and the from encoding, which is the big 5 Hong Kong supplementary character set, the output span, and of course the UTF-8 from encoding. We have an error handler here. We have the states. We have both states from the from state and the to state. And we have both error handlers. And so basically, we wrote this text transcode 1 function that gives us a shortcut between big 5 and UTF-8. And so if that's available, we'll just call that instead. Right? There's no reason for us to do the whole loop and do the encode 1 and then get to the intermediate and then take the intermediate and put it in and then put that and then have it decode from the intermediate to the output and do all this other work. No, there's no reason for all that labor. Right? Just we give this we give a direct singular way of making this work out. Okay? And so this is essentially what it looks like, right? So we do if constpr, has ADL transcode 1, right? So this part up here, right? We do if constpr. So what if constpr does is it says it checks that this condition is a compile time condition, right? So this condition does not execute any runtime statements, all compile time stuff. And if that works, then what we do is we drop into this upper blob here, right? And then basically we get a result from the text transcode 1, we give it the input, we give it the from encoding, we give the output, we give the to encoding, we give the from handler, the to state, and the from state. And then from there we basically check, is the error code not okay? And if that's the case, then we bail. Otherwise, we use the result directly, right? Rather than going through any intermediates. And that's it, right? It's a very simple extension point, right? And if we fail, then we just go down here back to the basis loop and everything's fine, right? And that's okay, right? We want that to be the case, and that's perfectly fine. That it is absolutely okay to do that. And again, so this covers one at a time transcode, right? And you might think, okay, one at a time transcode can't be so important that you devote an extension point to it, but it does, because the whole point is that the one at a time transcoding that we do, it improves the speed of the basic loop, but it also helps things like ranges, right? If you wanted a lazy range over UTF-8 that produced big 5 Hong Kong supplementary character set units of information, right? Every time you got big 5 code units out, right? Every time you iterate over the transcode view, right? And there could be a number of different reasons for this, right? Like you don't want to pay the memory cost of doing this bulk conversion all at once and storing it somewhere in like a vector or something. And so there's many different use cases for I only want a view of what this stuff is. I don't want to do the whole bulk thing, right? And so in this case, you can get gains out of this in the transcode case, right? So you can get gains out of this and make it work faster. And in this case, especially if you have the extension point available, in a header or in a module where it's visible, then optimizations can kick in and you can get a lot bigger gains. Zach Lane, his Boost.txt library, which recently went out for Boost library review, actually employs some of the same techniques to do faster conversion between certain conversion pairs. And he had an iterator-based approach and a range-based approach, and that still, when he did his benchmarks, got competitive, right? He got competitive results to current gen, SIMD and everything else, right? Because the compiler was able to see through everything and do the right thing. So we want to give people the power to control the performance characteristics of this transcode view, right? Because again, what transcode view will do is that it will set up an iterator, and basically it will just do that basic loop, but it will allow you to basically iterate it over it, 1 point at a time, right? So you can improve the performance of views by overriding transcode 1, right? And that's useful. That's just generally useful for the whole ecosystem, right? So that's the one at a time case, right? But how do we enable bulk improvements, right? We saw that quote from Rich Felker that said, it's about half as fast, right, to do things one at a time, right? So we really need to do bulk inversion, right? So how do we enable that, right? And it's the exact same principle, but you're just supposed to use an extension point, right? And so what we do is we create a place that you can override. And to illustrate this, we're going to go back to something that we talked about in part 2 of this talk, which is any encoding. Right? Any encoding is this very interesting thing that I spent a lot of time talking about how you set it up and how you make it possible. In this Meeting C++ 2019 talk, you can click on this here and it'll take you there. But that's essentially what this is. And the whole point about any encoding is that it has a unique set of challenges. And one of those unique set of challenges, I talked about one set of unique challenges which related to the state and how you make it work, which is why the state is ... in this slide. I talked about some of those challenges, but there's additional challenges that we need to look at here. And so what any encoding really is basically stood function, but it's for encodings, right? So it has a constructor, and you hand it the encoding, and what it does is it flattens things out, right? So decode1 always takes bytes, right? And so that's how it erases the idea of whatever your code point type is, right? And then for encode1, it takes code points, in this case, Unicode code points, and it just outputs bytes, right? And that's how it equalizes the system, right? And so we do a bunch of shenanigans internally, and it does magical things to basically take your code points, code units, and basically input and output bytes that you can use. And of course, we have a gratuitously oversized max code points and max code units so that it can fit many different encodings, can work for this kind of runtime thing, right? So the any encoding, the internals, right? What it does is it type erases the encoding and stores it inside itself, right? So every time you call decode1, it basically unwraps the thing you stored in the any encoding, and then basically calls stored encoding decode1, right? It just, virtual function pointer, some magical SBO, whatever it is, we do that, right? Then for encode1, it's much the same thing. We unwrap it and we call the internal encode1 with, properly casted, pointers and ranges and everything else, right? And that's just how that works. That's just how that works. So what we do after that is we then go on to say, let's consider this idea of the basis loop, right? So let's say we want to call decode. We want to call a decode function, right? And so what happens is that in the basis loop, what we'll do is we'll call decode1 a bunch of times for the any encoding, and we're going to do it on 1,000,000 code points, right? So let's just run the mental logic here, right? I have a loop. I'm doing it 1,000,000 times. I get to the any encoding decode1 call. I have to unwrap it, which is overhead, do the actual real call after setting up all the pointers and everything else, and then after that I exit the call, right? And that's also overhead, right? And then I loop back and I do this all over again. Okay? So that's 2 times the overhead that we have to pay for entering and exiting this hard compiler barrier, this virtual function call, this function pointer, or some magical SBO, whatever it is, times 1,000,000. That's a yikes from me, dog. Any encoding is hidden behind this mask, right? And this mask serves as a compiler barrier. And that compiler barrier can pessimize your performance to hell and back, right? So you need a way of controlling that strongly so you don't have to worry about the problems that come with performance for something like an any encoding, right? So we can do better. Right? So what if we had this extension point called text decode? And if it exists, what we do is we call that instead of running the basis loop that calls decode1 a bunch of times. And what ends up happening is that we end up actually unwrapping the encoding once. We do the 1,000,000 code points in the actual call that we're supposed to, 1,000,000 times without any overhead, and then we exit the function. Okay? So it's just a typical inversion of the loop, right? So rather than doing the loop on the outside, we do the loop on the inside, right? And that's a much nicer flow, and it has a much better performance profile. Okay? And so this is the way that we go about and we enable bulk encoding. And so what basically happens is if you write any of these friend or these friend or hidden friend or free functions on your encoding object or next to your encoding object in a way that ADL can find it, what happens is we pick it up. So we pick up text transcode 1 for the ranges and for speeding up the basic loop case. We have text decode and text encode, which just whenever you call encode or decode to do the free function conversions, right, we'll pick up and call that for you. If you have text transcode, we'll also override that, like we showed was possible with text transcode 1. And we'll also do this for decode count and encode count, as well as validate and validate as, right? And so as long as you care about the performance profile of any of these, right, you can override them and do the thing that you want to do. The library will obviously call them for you, right? So for any core loop or ranges that we write, we will call text transcode 1 if it's applicable, right? When you call the library function decode and encode, we will reach out and call your text decode and text encode function calls, right? Similarly for transcode, for decode count, for validate and validate as, we will always do that step for you, right? So you don't actually have to worry about how to call it or anything. You just have to write the function to do the work. And this means that everybody speaks the same language, right? So here's an example that's pulled out of a BoostBeast server, right? So I have an any encoding, that's the from encoding, right? And this is a BoostBeast server, and I get a message from the WebSocket that says, hey, excuse me, sir, the data you're going to get is in this encoding, right? So that could be UTF-8, that could be Big 5 Hong Kong supplementary character set, that could be GB 108030, that could be one of the GBK encodings, that could be one of the Tamil encodings, it could be one of the Russian encodings, one of the Russian code page encodings that are common in Windows and everywhere else, right? So I init the any encoding with this encoding later, and then, obviously I have the response, the request and response body that gets filled up every time we do one of these boost calls. And so when BoostBeast calls on read and we get the error code and we have the number of bytes transferred, I'm skipping a little bit of the boilerplate here. There's a lot more that goes into this, but I'm skipping the boilerplate here. Basically, we get the res body data that we received from the bytes transferred to the data that we have, and what we do is we create a unbounded view over the converted body, which is the vector, which is a string that stores all the data. And what we do is we create our own UTF encoding. That's the 2 encoding, right? And then we go from that encoding to the different encoding, calling txt transcode, right, the text library. And the whole point about this is that this will call your extension points if they're there, right? Internally, because it's part of the library implementation, I will unwrap this any encoding, right? So in the case of Big 5 Hong Kong supplementary character set, we will unwrap this for you. And once I unwrap it and get to the internal, say, Big 5 encoding, I will then check if there is a UTF-8, Big 5 to UTF-8 encoding ADL extension scheme. And if that happens, what I will do is I will call it for you. And so this means is that in your applications, all you have to do is keep writing text transcode, right? So you can write your whole application, right? And you can use text transcode, you can use decode, you can use validate, whatever else, and you say, oh, I need to speed this up because the performance is horrible. And instead of going back to every single call in your server, in your application, in your whatever else, you just write one of those extension points, like we had shown before. You write any one of these extension points, any of the ones listed at the right-hand side here or beneath here, and we will pick it up for you, and it will just automatically be called. The minute you implement one of these extension points, we will immediately call it for you, and that means that your entire code base can be sped up. Right? So without you doing any extra work, without you having to go examine every call site, we will immediately pick it up and give you everything that you asked for, without question. I want you to understand the power of that, right? You can get the same performance characteristics if you're using Express. old as dirt, that has been around since the aughts, since the 2000s, that we're still fixing for, right? And you have to wonder, right, like, is that a good use of anyone's time? My assertion is no. That's not the case, right? You don't want to be applied to a proprietarily controlled standard library, or a standard library that's out of your control, or a standard library that you're not going to update because you're stuck on rel 6 or rel 5, God forbid, right? And so what happens is that now it's an open ecosystem, right? Somebody can write a library where all they do is overload all of the different ADL extension points and write a bunch of encoding objects and give you not only the encodings you want statically at compile time, that in objects that you can interface, but also make them fast for you as well, right? So if you want to write, so even if the standard doesn't ship, right, like Big 5 Hong Kong Complementary Character Set, if they don't ship UTF EPSIDIC, if they don't ship EPSIDIC character code pages, right? If they don't ship Latin 1, if they don't ship, God forbid, all of the different code pages that have come out of Microsoft and IBM over the past 20, 30 years, right? You don't need to wait for the standard to figure out what's useful and necessary. You can just implement your own, and that's all you need to do. And so you can make them fast for encoding pairs that you care about once, and everybody, whether everybody in your case is just your application because it's a proprietary application, or it's the entire ecosystem because you released an open source library that, say, implements all of the what working group, the web what working group encodings, right? You can make everybody benefit. And that means that it's an open, instead of being a closed system that you have to crack open icon V to add new encodings, or bother your standard library implementer about how to get access to some proprietary or buried in the details locale encoding that's not standard anyway. You don't have to do any of that anymore, right? It's an open ecosystem. And it has usages, right? Some people are wondering, like, okay, well, how could you possibly, there's only so many encodings, and how could you possibly have ways that they're important, right? How could you possibly have ways that you want to override this? And yet, we see as recent as 2019, people writing blog posts about how to get better, faster, more wonderful validation and conversion routines and everything else, right? So it is imperative that we have an open ecosystem, right? Because again, how many times have you heard about the ABI problem and, oh, we can't change things because that would break the user? Well, now it's not up to the standard library anymore. It's not up to their ABI. The end user can decide when it's time for them to upgrade their validation routine, or when it's time for them to upgrade their UTF-8 or UTF-16 conversion routine. And it's no longer in the hands of the standard library anymore, right? They can implement whatever quality of implementation they have for the small amount of encodings that we wish to standardize, but you, as an end user, can still have all full control to do everything you want to, whether it's fast validation with the stuff that Daniel Lemire wrote here, or if you want to use Bob Stiegel's fast UTF-8 conversion with the DFAs that he wrote and the amazing work they did with intrinsics and everything else, now you have that accessible to you, right? And if you also have other uses, right, you can use platform-specific APIs, right? So if you are relying on icon V, you can plug icon V into this interface. It works just fine, right? You can plug multi-byte to widecar, right? If you detect that you're on Windows and you're going from the current car locale encoding to the wide character code, right? You could just plug in multi-byte to widecar because you know how that works, right? Similarly, you could do the same for Apple's ecosystem and other places as well. And so what happens is that you can wrap everybody's garbage up into something that speaks the language and something that the standard understands without having to actually explicitly ask the standard for permission. And of course, there's tons more use cases, right? And what this affords us, what this Lucky 7 design affords us with these ADL extension points is it affords us infinite scalability, right? No more, God, thank God, no more WG21 papers. None. Nada. You are in control, right? Standard has bad quality of implementation, override it. Billy O'Neill doesn't have time to make the UTF-8 to UTF-16 faster and you can do a better job, override it. Jonathan Wakely doesn't have time to support some crazy kooky encoding that was part of glibc, but he doesn't care for it, override it. It is no longer the implementation's job to always provide you the best QOI. You can override it. You can get something better than what has been given to you before. And again, you can just make that encoding yourself, right? So if you need the Tamil standard for for code interchange and exchange, right, then you can just make it. Congratulations, it's now part of your application, and you are free from whatever garbage the standard wanted you to do, right? You don't have to go appeal to Boost for something. You don't have to go ask the standard. You don't need to write some paper, say, please, consider my legacy encoding because it's important and I have a bunch of government data in it and I need to port it out, or I have a bunch of book data and I need to port it out of this database. You don't need to ask them permission anymore. And so no company owns you. You don't need to go to say, well, please, Mr. Microsoft, please, sir, I need this big encoding. Oh, please. Right? You don't need to go and ask this. You don't need to go ask WG21. You don't need to go to standards committee and be like, well, please, committee senpai, accept my papers for my encodings. Ooh, you don't have to do that anymore. None of that is there. And what it does is it starts here with us, with no committee telling us what to do, no implementer veto due to API. It belongs to us, we the people. We are no longer held hostage, no longer shackled to what someone thinks is a good idea for us. No glibc, no musalibc to decide that there are encodings that they want to support and everyone else can go to hell. We are the masters of our own fate. We are the arbiters of our own destiny, the captains of our own ships. We do not have to go down like we did in the past. We don't have to suffer at the hands of the cloying indifference in the face of the hardship, left to struggle on our own without any support. We no longer have to accept the things that we cannot change and the broken past, but we will change the things that are unacceptable to us. We will have a future that is worth getting to, and every cash register's receipt, every registration form, every tiny system on a chip and glorious supercomputer will be able to spell our names. Not just the English names, not just the European names, not just the Chinese names that they felt they had time for. Every system will spell our names in the way that they were spelled by our parents, the ways that we spelled them ourselves. It belongs to us. We will not be left behind. We will not be forgotten. We will not be lost into systems that govern us, and they will belong to each and every one of us. All of us.
Row, row, fight the power. Row, row, fight the power.
Thanks for listening. I appreciate that you took this journey with me, that you wanted to see what the encodings were like, what the ADL extension points are like. I greatly appreciate it. I wanted to thank, of course, my wonderful individual patrons and sponsors, except this is a bit of a psych, because this is the old list of patron and sponsors. This is the new one. Thank you so much to the person who shouted me out in Deboogi's list. And I don't know, it just had an explosion of support after that point. And thank you so much to everybody. Some familiar faces here, some new ones. Some people who are too shy and they want to keep it private. And some people who, of course, are out in the open. Cy Brand, especially, Tom Honerman, who's encouraged me in SG16, Matt Godbolt, who's always sent support, a bunch of people from the Soul 2 Discord, No Fate, I see you. Thank you so much to each and every one of you for your emails, for your support, for stopping by the Discord. I appreciate every single one of you. You are literally making sure that I can still go to school and put food on the table for myself and eat and not starve and die. Thank you. I appreciate every single one of you more than you know, and I love each and every one of you. Also, I want to thank the Netherlands, the NEN organization. They actually helped onboard me for the C committee, and such to the point that I'm actually the product editor now for the C. What this basically means is glorified title where I get to put the standard together. But it does mean that I get to read the standard from cover to cover, which is something that I kind of slightly been avoiding doing because it's kind of a real slog to do. But it's just kind of the way the cookie crumbles. So yeah, check out NEN. They have their website here. You can go check them out. If you're part of the Netherlands or maybe Netherlands adjacent, maybe you can ask them and maybe they'll help you out go to standards as well. They participate in ISO and a bunch of other places as well. I also want to thank people for the very media used here, particularly the last one, Admiral Baru. So my friend actually sent a message for the elements of transcoding that I had written with that silly crayon and that panda. That actually comes from Admiral Baru, his stream. And so somebody actually sent, it was crazy. Somebody actually sent this guy who has like 8,000 people and like thousands and thousands of like subscribers to his Twitch channel and everything else. They sent him a direct message on my behalf and said, hey, this guy showed me his presentation, it looks pretty cool. Can you let him use the emotes because I want him to use it there. And he actually said that it's actually totally cool if we can use the emotes for non-commercial use for this presentation. So thank you so much to Admiral Baru. He has a stream there. It's twitch.tv/Admiral Baru with no space. Check him out. I had a few laughs when he was there, and I got to use some of those emotes, which made for a good little chuckle. Of course, we still need your help. We have a plan for text in C and C++. So you can go to those links there and you can check it out. You can obviously support the plan by going to the phd.github.io/support. And there's a bunch of different ways that you can tip to the cause or sign up to be a sponsor for GitHub Sponsors or Patreon, whatever your flavor is. We're there. And of course, you can watch me struggle into this on twitch.tv/Shepherd'sOasis. Where once my computer gets fixed, because it's been out of commission for it's going to be about a month in a hot week, and I'm still waiting for an RMA on a GPU that exploded. You can watch me there, and that's where you can see me struggle. The last thing we did was actually re-implement std vector. We passed all of libstd C++'s tests, so we actually have a standards conformant vector that is no except safe. Like, it actually is completely no except, so it's actually suitable for game development and low and embedded devices. It's actually pretty nifty, and I enjoy it. Of course, filing, hardening, testing, performance. We're also kind of known as text people scripting on small devices. Whatever's your flavor, whether it's SOL2 related, Infoware related, we got you covered. Let us know here. Send an email. So again, if you don't feel like just contributing directly or watch the stream or subscribing to the Twitch, you can always just ask for something a little bit more concrete and hard. We'll set that up, and please come to us. And that's it. So I'll be here for questions, so please feel free, and thank you so much.
Thanks for this wonderful talk. That was definitely a lot of very interesting stuff. We have just 3 minutes left, I believe, for questions. We have quite a few questions on the Telegram chat, so maybe I'll just do a couple, and then we're going to continue in the Zoom chat. So one is, the handled error stuff looks quite specific. So they write, I expect to have some customization point. For example, passing a std function as a callback inside of encode decode result.
So the way that errors are handled is that the handlers themselves don't get passed through the encode and decode result types. They're instead passed directly when you call the transcode function or the decode one function or any of those, and it's just used there. And what happens is that I explain this a lot in the meeting CS Plus talk. Again, there's limited time. I can't explain everything. But the way it works is that it allows for you to basically do whatever you want inside that callback. So you can throw an error if you want to. You can add a replacement character. You can log, of course. You can terminate if you weren't expecting that. And so the basic idea here is that the handler is passed to the function. The encoding calls your handler when something goes wrong, and your handler decides how to proceed. And the reason it does this is because it's a value-based error handler, in that it passes into the error handler. It passes you all the necessary information to construct a result. So, for example, if you want to do a replacement character, you can insert a replacement character into the output stream and then return the result as if nothing went wrong, right? And that's how replacement characters work in that particular case. So that's what is done there. And so I hope that answers your question. But again, the handler isn't part of the result type because the function is responsible for calling it. It's not given back to the type, and you don't have to call it yourself. Yeah.
Okay, thanks. Yeah, there's another very interesting question. What about multi-threading support? Like, for instance, for basis loop, one decoding thread, one encoding thread. Would something like that be possible?
So yes, that would be possible, but I'm not trying to include multi-threading into the core API right now, right? Because again, there's a lot of different trade-offs that a person can make for the case of asynchronous work, right? So someone might be able to decode on 4 threads and encode on 4 threads, right? And trying to split that up and make that decision for you will only really end up getting on your nerves, right? And we've had experience with this before in the standard. We made something called std async, which is I think std async or std launch or something like that. But basically, the whole point is that was a very simple function that would you pass the function to it and it just magically dispatched work somewhere, right? And the problem is that was so underspecified and so hard to control that it actually ended up getting in the way of the majority of the people who are trying to do asynchronous work and didn't actually provide anything to the table. So rather than try to get in anyone's way with this, I'm not going to try to build any asynchrony into the API itself, and instead let people farm out, the call to wherever else and do the splitting up themselves, right? I think in the future, maybe we'll have some room to make some improvements on that. But right now, we really don't have the kinds of abstractions or power to very accurately map to the kind of asynchronous work that people want to do. So yeah, so there's no multi-threading, no asynchrony, no race condition you have to worry about. It's all, it's all single-threaded stuff, and you can farm out the work however you feel like it.
Cool. Yeah, so it looks like we got another extra 2 minutes. So there's a question about slide 8.12, if you can, I don't know if you can see that.
Let me just, 8 point, here we go. Okay, yeah, so this is the boost
example. The question is, where is the concrete encoding for session for encoding defined?
Right. So the encoding we take here comes from the from this any encoding that we're using, and I put it in a comment here, but basically this gets init earlier from an earlier call where it puts basically either UTF-8 or UTF-16 or whatever else that you've decided or you negotiated with your with the connection what should be sent down. To go back a little bit, I can show here there's a constructor for any encoding that takes any other encoding object, and you can basically put your encoding in there, right? So you can put UTF-8, you can put UTF-16, you can put Big 5, Hong Kong supplementary character set, and that's essentially how we get to the place here where this from encoding, this any encoding, has the proper encoding, right? I'm not showing you everything here because, again, I go through it in painstaking detail in that Meeting CS+ 2019 talk, but that's where that comes from.
All right. I'm not sure if we have time for another question.
I don't know if there's a quick one I can probably try, but...
I believe it's better to leave it for the Zoom session.
Okay.
Okay, so thank you very much, John, for your talk, and thank you, Zoomler, being expert at it.
Thank you. It was great to be here.
Very nice to be here, yes.